Hello, my name is Arthur Kay. I'm the Precision Analog Applications Engineering Manager, and I support products like op amps, instrumentation amplifiers, references, and other analog products. Today we're going to talk about input and output swing limitations with op amps. Over here we have a Realworld demo, and we're taking an amplifier that's in a voltage follower configuration, applying a triangle wave to the input, and the output is shown below in blue. The input is nice linear triangle wave, but the output is linear on the negative half cycle, but distorted on the positive half cycle. What causes that distortion and clipping, and how can we avoid it? Let's look at some slides for further detail. This slide shows the common mode voltage definition. The common mode voltage is the average voltage applied to the two inputs of the amplifier. In the case of an op amp, the two inputs are essentially at the same potential with a small offset between the two, so effectively you can really see the common mode voltage on either input. Input and output swing is really referring to the common mode range on the input and the output swing limitation. The common mode range is relative to the positive supply and the negative supply, and when you exceed that range, the output will become nonlinear. The same thing with the output swing. The output can swing close to the positive supply and close to the negative supply, but will become distorted and nonlinear if you exceed the output swing specifications. Let's look at a data sheet. How is this defined? We have the input common mode range given here, and we have a minimum specification and a maximum specification, and they're relative to the power supplies. The negative supply is 0 volts in this case, so 0 volts minus 0.1 gives us a negative 0.1 volt for the minimum common mode voltage. The positive supply is 5 volts minus 3.5, so the maximum input swing is 1.5 volts. Going above 1.5 or below negative 0.1 will cause a nonlinear output. The output swing is given here, and it's the same kind of method relative to the supplies. In this case, the negative supply plus 0.2 is 0.2, and the positive supply minus 0.2 is 4.8. Going below 0.2 or above 4.8 will cause the output to be nonlinear or clipped. What's inside the amplifier? This is an input stage. Of course, they're different from amplifier to amplifier, and this is simplified, but the point is there are transistors that will saturate and cut off as we approach either of the supplies, and this is what causes the common mode input limitation. The output stage limitation is caused by diode voltages and saturation voltages in the output stage. Different topologies or different amplifiers will have different topologies, and some will get closer to the rails than others, and different technologies sometimes will offer advantages as well. Here's an example of two different circuits. This is an inverting amplifier. Notice that the non-inverting input is grounded, so the inverting input is essentially at ground potential as well, and the common mode voltage remains constant regardless of what the input signal is. This is a good topology to use to avoid common mode limitations. The non-inverting topology, the input signal and the common mode signal track each other, and so with input signal changes, the common mode voltage will change, and you have to be careful not to violate the common mode range limits. Here's a real-world example. It's a buffer. We're applying 0 volts to the input. We expect to get 0 volts out or just some small offset, but we get hundreds of microvolts, hundreds of millivolts, whereas it should just be microvolts out. What's the problem? The input common mode range, just using the same techniques we talked about with a 5 volt supply and a ground, is negative 0.1 to 1.5, and the input signal is 0, which is right between these, no problem. The output, using the same methods, 5 volt supply and ground, is 0.2 to 4.8, and we are outside of that because the output wants to go to 0 volts, and that's below the 2 volts, so it's out of range, and that is why we're getting hundreds of millivolts rather than microvolts out, and it's a violation, nonlinear signal. Let's look at another example. Starting with the output, we have the output range with different supplies, plus and minus 2.5 volt supplies. We have plus and minus 2.3 volt limits. No problem here because the output wants to be 0 volts. It's not outside of this range. What about the input? Well, with the input, we have a 0 volt input, and if we look at the plus or minus 2.5 volt supplies, the range of the input is minus 2.6 to minus 1, and 0 is outside of that range. So it's a violation. That's why we have hundreds of millivolts out instead of microvolts. Let's take a look at a simulation of this. You can use simulation to actually solve this problem as well. So using Tina Spice, which is a tool that TI provides for free, we can do a transient analysis. This is, by the way, the same circuit we actually built and measured earlier. So we run the transient analysis. We get a bunch of curves. Let's separate those curves. And we have the input signal, which is a plus or minus 10 volt triangle wave. The input common mode range using the data sheet is minus 10.1 to plus 6.5. So a 10 volt peak is going to violate that range on the positive end. And we see that the output becomes nonlinear and in fact clips in the circuit. Let's take a look at the real world circuit again. So in the real world example, you see the same thing. We've got a nice linear 10 volt triangle wave in, and the output is distorted. In the case of the simulation, it was perfectly clipped, but you can see that in the case of the real world, it's clipped, but it's also distorted. Really what the simulation is telling you when you see a clip is not that that's exactly how the circuit is going to look, but that we're going to have nonlinear performance in that region. So in summary, you can measure, simulate, and calculate the common mode input and output swing limitations for amplifiers. And using these techniques, you can avoid these problems. So for further information, please see the attached links. Thank you.